Hello everyone, this is the presentation for the course Topics in Data Science. My name is Gao Gao. I am a PhD student of Computer Science Department at UMass Lowell. I will talk about deep contextualized word representations. This paper was published in 2018. Because of my research field is about human-computer interaction, so I didn't have much knowledge about the language model in NLP. I'm not sure I could be 100% to understand the paper very deeply. I have found some learning materials of this paper and several explanation lecture of this paper. I just try my best to understand it and give myself explanation of what I learned from this paper. Before I talk about this paper detail, I will talk about some background knowledge of language model embeddings, which I had tried to begin to learn. I have several questions in my learning process. The first one is, what is NLP? And I find some definition from like Google or the other website. The natural language processing is a subfield of linguistic, computer science, information engineering, and artificial intelligence concerned with the interaction between computer and human language. In particular, how to program computers to process and analyze large amounts of natural language data. The second one, what is language embedding and what is embedding from language model? As we all know, language is very complex. The context can completely change the meaning of the individual words in a sentence. Here I have one example. The sentence, "That's right," and another sentence, "Please turn right." We could see the words are the same but have a different meaning. We can use this very easily to decipher this complexity in the language. But if we create a model to understand the different meaning of the nouns in the given surrounding text, it's very hard. The third one is word embeddings. So now we have some word embeddings tool like the word to vector, fast text. They can just represent per words, so they cannot capture how the meaning for each word can change based on context. Let me talk about this paper. In this paper, I will talk about 5 parts: introduction, model approach, evaluation of the model, analysis, and conclusion. The first part, introduction. So now we know the natural language was very difficult to work directly. It could better transform the representation to something like machine readable. So learning high quality representations can be a challenge. The pre-trained word representation ideally model should have the characteristic like this. The first one is complex characteristic of word use, and it should have uses vary across linguistic contexts. So in this paper, it's introduced a new type of deep contextualized word representation, which is different from the traditional word embeddings. The paper used the vector derived from bidirection LSTM that is trained with the coupled language model objective on a large context corpus. So it's called embeddings from language model. This model in the sentence that they have a function of all the internal layer of the bidirectional language model. Combining the internal states in this manner allows for very rich word representations. The previous approaches for learning word vector only allow a single context-independent representation for each word. So we will try to know the contribution about this paper. So it have the leveraging language models to get pre-trained contextual representation, and it find the embedding from the language models. The crucial finding for this paper is they use the higher level LSTM internal state capture context independent aspect of the word meaning. And this representation can be easily integrated into existing models and significantly improve the state of the art across the 6 challenging NLP problems. The 6 challenging NLP problems I will talk it later. The model approach. So the embedding from language model word representations are the function of the entire input sentence. They are computed on top of 2 layers bidirectional language models with the character convolutions as a linear function of the internal network states. This allows to do the semi-supervised learning, where the bidirectional learning model is pre-trained at a large scale and easily incorporate into a wide range of existing neutral NLP architectures. So we will see this picture is bidirectional language models. In the embedding from language model, it uses a two-way LSTM language model consisting of forward and backward. So I listed two, like the formula of the language model. One is from the forward and the other is backward. The objective function is to take the maximum likelihood of the language model in these two actions. So after pre-train this language model, the embedding from language model is used as a word representation according to the following formula, which is to sum up each intermediate layer of the bidirectional language model. The simplest can also use the highest level representation as the embedding from the language model. So let us talk about the embeddings from the language model. This is a crucial part of this paper. So when performing a supervised NLP task, embedding from language model can be directly spliced into the word vector input of the specific task model or the highest level representation of the model. To sum up, unlike the traditional word vector, each word corresponds to only one word vector. The embedding from language model uses a pre-trained two-way language model and then derives context-dependent current word representations from the language model based on the specific input. So the input could be the different context. So the representation of the same word is not the same, and then added to specific NLP supervised model. So here, this is the scalar parameters, and this part is the softmax normalized weight. It will calculate the overall softmax normalized weight to calculate how is the embedding from the language model work. So using the bidirectional language model for supervised NLP tasks, a pre-trained bidirectional language model and a supervised architecture for a target NLP task. It's a simple process to use the bidirectional language model to improve the task model. Run the bidirectional language model and record all the layer representations for each word. Then let the end task model learn a linear combination of these representations. So use the bidirectional language model for supervised NLP task is benefit to at the moderate amount of drop out of embedding from language model, and in some cases to regularize the embedding from language model weights to the loss. This imposes an inductive bias on the embedding from language model weights to stay close to an average of all bidirectional language model layers. So what is pre-trained bidirectional language model architecture? The pre-trained bidirectional language models in this paper supports joint training of both directions and add the residual connection between LSTM layers, which highlighted the importance of using bidirectional language model over forward only language models and large-scale training. The bidirectional language model provides 3 layers of representations for each input token, include those outside and training set due to the purely character input. Once pre-trained, the bidirectional language model can compute representations for any task. In some cases, fine-tuning the bidirection on domain-specific data leads to significant drops in perplexity and an increase in downstream task performance. So now we will talk about the evaluation of the model. In the evaluation part, the work evaluates embeddings from language model in some common NLP tasks. It has 6 tasks here. The first one is question answering, textual entailment, semantic role labeling, coreference resolution, named entity extraction, and sentiment analysis. First, they built different models for each task as a baseline, and then joined the embedding from language model. You can see that all 6 tasks have been proved after joining embeddings from language model. with the data, and the average can be increased more than like 2 percentage point, and the final result exceed the previous advanced result. So that will say, which if you use the embedding from language model, it have a better performance than if you not use. So the analysis part. In the analysis part, we can see that the effect of using all layer is better than using only the last layer as the embedding from language model. On the input or output plus the embedding from language model effect is not conclusive. Different tasks may have a different effect. So here, the alternate layer weight schemes. The lambda is regularized of the embedding from language model weight to the loss. So the large value such as lambda, if the lambda same to 1, is effectively reduce the weighting function to a simple average over the layer, while smaller value, if the lambda like 0.001, although the layer weights to they are different. So where to include the embedding from language model? Including embedding from language model at both the input and the output layer for the SNLI and SQUAD improves over just the input layer, but for SRL, performance is the highest when it includes that just the input layer. So what is the information captured by the bidirectional language model representation? It's for 3 parts. The first one is word sense disambiguation. The second one is POS tagging. The third one is implication for supervised tasks. So now we will talk about sample efficiency. So adding embedding from language model to a model can increase the sample efficiency considerably, both in terms of the number of parameters updates to reach states of the art performance and the overall training set size. After adding embedding from language model, the model exceeds the baseline maximum at epoch 10. It's like 98% relative decrease the number of the updates need to be reach the same level of performance. So we could see here the accuracy and the SNLI accuracy and the SRL. So this training set size is vary from 0.1% to 100%. So in this figure, is a comparison of the baseline versus the embedding from language model performance for the SNLI and the SRL as the training set. we could see that is increased with the baseline. We could see also the baseline with the slash line, and the one with the embedding from language model use the solid line. So with the embedding from language model is much more better. In additionally, we could see the embedding from language model can enhance the model use smaller training set, more efficiency the model without embedding from language model. So the performance of baseline model with and without the embedding from language model as the percentage of full training set is have a very big improvement. So in the SRL, this graph, this case, the embedding from language model with the 1% of the training set has about the same F1 as the baseline model with the 10% of the training set. So it have not that much effect of this model. So the visualization of learned weights. This figure shows the visualization of softmax normalized bidirection language model layer weights across tasks and the embedding from language model locations. Normalized weights less than 1/3 and hatched with the horizontal lines, and those greater than 2/3 are speckled. As the input layer, the task model favors the first bidirection LSTM layer, so the core reference and the SQUAD. This is strong favor, but its distribution is less picked for the another task. The output layer weights are relatively balanced, with the slight performance for the lower layer. So the conclusion. It have the conclusion is about how is the paper by using the bidirection language model and the embedding from language model. The general approach for learning high quality deep context dependence representation from the bidirection language models. And this approach allows large improvements when applying using embedding from language model to a broad range of NLP tasks. So through the experiment is confirmed the bidirection language model layer is efficiently encodes different type of syntactic and semantic information about word in context, and is using all layers improve all overall task performance.